Okay, well, welcome everybody. Sorry about the change in plans today. Just was trying to err on the side of caution, but I will feeling a lot better. So I think I'll be back in campus on Thursday. So we should be back in person. But thanks for your understanding about today. So I'm just on our Canvas site just to let you know what the plan is for the week before we get started. So the plan for this week is to talk about material in chapter 6 of our text, Chiara and Hesterberg, which deal with estimation methods. The ones that we'll take a look at are maximum likelihood estimates and the method of moments as well. So today we'll take a look at maximum likelihood estimates that are abbreviated with an MLE. Everything that we're going to do this week is more theoretical, more analytical. We're going to be doing things by hand, doing some calculus, maybe doing some algebra. So we're not going to be using R at all today. So all I put up was a couple of PDF documents. So you're welcome to kind of mark those up. That's all I'm going to do is I'm just going to annotate those notes together today. And it'll be the same plan on Thursday. We'll just be working with a PDF document. So this is a little bit more theory as opposed to doing some simulation-based methods. Today you kind of watched the video with an introduction into that. So we'll pick up from that point. And then on Thursday, you've got a video for the method of moments. And so as far as the work goes for this week, you've got, a quiz for Thursday. And then you've got a homework assignment, which is due this Thursday. All of that material was covered last week. And then the material that we're covering today and on Thursday will be on a homework assignment, which is going to be due next Thursday on the 27th. So we're going to be back to kind of Thursday homeworks. But any questions about that? Okay, so I'm going to share my screen. I'm just going to open up this document right here, which is worksheet 14, dealing with estimations using MLE. So let me open up my iPad and share that with you. Okay, so hopefully this is working. Let me know if for some reason you are unable to see the screen here. So here we're working with, this is worksheet that's called 14 estimation MLE. So the goal here is going to be, we've got some distribution, some theoretical distribution in mind. And given the data that we collect, we would like to come up with what is the most likely estimate for the value of the parameter or parameters that determine that theoretical distribution. So the example that we started taking a look at for the reading quiz for today is this first example over here, where let's say we're trying to determine whether a slot machine seems faulty or not based on the number of jackpot payouts that it's paid out over a week. And so in the video, we kind of talked about doing one with normal distribution, doing one with this example, and we came up with Poisson distribution seems to make sense for this data because the data pretty much follows a trend where the most likely thing is we don't have that many jackpots, but as the X gets bigger, as the number of payouts in a week gets bigger, we expect that to occur less and less likely. So any questions about, sorry, my ear is like staticking out. Any questions about where this Poisson distribution comes from? Okay, So then what we would like to do is think about what is the probability of getting this data that we've observed over here. So with a Poisson distribution, just recall, we have a PDF that I'm going to denote f of x lambda, which is equal to lambda to the x e to the minus lambda, all divided by x factorial. And here we're dealing with a discrete random variable. So x is things like 0, 1, 2, 3, 4. So the factorial makes sense down there. And one thing I want to point out with this notation is we usually put the variable first, the random variable first, and then we follow that with a semicolon, and then we indicate what the parameter is. And sometimes our functions we've seen have more than one random variable. We've seen joint distributions. So you might have an x and a y and a z. And sometimes we've got more than one parameter in a distribution, like a normal distribution where we have a mean and a standard deviation. But for a Poisson distribution, we've just got one random variable and we've got one parameter, the rate parameter lambda. So remember here, lambda is telling us the average number of, in this case, occurrences, which would be jackpots in 1 week. Okay, any questions so far? So if I want to, this is a discrete random variable. So if I want to calculate what is the probability that x is equal to 1 and x2 is equal to 3 and x3 is equal to 4 and x4 is equal to 8, right? Because this is, we're assuming that these are independent random variables, then the product of this and that and that and that is just equal to the probability of this times the probability of that and so on, right? So I can break up this and probability into saying that the probability is equal to the probability that x1 is equal to 1 times the probability that x2 is equal to 3 times the probability that x3 is equal to 4 times the probability that x4 is equal to 8. I'm just going to open up a fresh page with this stuff. Okay. So again, our goal here is we would like to calculate what is the probability of getting this sample. Okay, and our sample were those 4 observations. And so first, we're just using the fact that these are independent random variables to write out the product. And now we can use our PDF, right? Which when we're dealing with a discrete random variable, this tells us the probability of getting X. So that means all I need to do here is take and plug 1 in for X to figure out what Px of 1 is. So this is going to be lambda to the first power, e to the minus lambda, all over 1 factorial. I'll put the 1 over here just to be clear. And then I've got P of x2 is equal to 3. So that would be lambda cubed, e to the minus lambda over 3 factorial. And then Px sub 3 is equal to 4. And then finally, we had P of X4 was equal to 8, I believe. We get that. And so the probability of all those things happening at the same time would be the product of these 4 probabilities. So I'm just going to say the probability of observing our sample would therefore equal the product of these. So I am going to add up all of my lambdas. I've got 1, 3, 4, and 8 of them over here. So that gives me 12, 15, I think we've got 16. Then we can take and add, or at least multiply these terms together. So this would be e to the minus 4 lambda. Then on the bottom, we've got 1 factorial times 3 factorial times 4 factorial times 8 factorial. Okay, so any questions on what we did or how we did that? Feel free again to unmute, chat, whatever you prefer on Zoom. Okay, so great, so that puts us over here. And now we can define what's called the likelihood function. So the likelihood function is a function which gives us the likelihood that we would get of getting a certain parameter, a value for our parameter, given the observed data. So it's like a conditional probability. So we're saying, given that we've observed all of these values, x1 up to xn, what's the probability that our parameter, in this case, we're calling it theta, takes on certain values? What's the probability that theta would be 1, 2, 3, 4, so on? And our goal in this process is going to be, we are going to find a value for our parameter that is going to be, that's the most likely value of that parameter. So given our data set, we want to find the most likely value for the parameter lambda. So in other words, in this case, given these observations that we have, what's the most likely value for the number of jackpots that gets paid out in 1 week?
So I have a quick question.
Sure.
So is lambda and theta representing the same thing, but just one's like how are they related?
Yeah, so in general, we typically use Greek letters to denote a parameter. So parameter are things that describe a population. Let me just kind of write some of this down. So parameters are these kind of fixed values that summarize a population. And we typically denote them like in absence of an example, the generic term is like theta. Okay, so just like in absence of an example, we typically use X as our input in calculus, right? So here's like our parameter. But typically we do use Greek letters for these. And then we have an estimate for this parameter. And when we think about estimates, we put a hat over it. So in this case, our parameter for Poisson distribution, our parameter is lambda. So that's the kind of default that people use when they're describing the rate parameter for a Poisson distribution. But when you see things defined more generally, they'll typically use theta as the parameter. Okay, so in this case, our maximum likelihood function is exactly what we just found over here. Except I want the entire thing. Except now we consider this ran out of room, a function of lambda, since we've fixed x1, x2, x3, and x4. And then what we want to do, now this is a function of one variable, right? And so now what we want to do is maximize this function relative to lambda. So we treat lambda as our variable since all of the values for x are fixed. And just to kind of see informally, you've got this little graph over here. What we're looking at over here is exactly the graph of this function. And then we would pick a value such as something close to 4 in this case, because that is the value of lambda that makes it most likely that we would observe this data. So we're trying to pick a value of lambda that maximizes the likelihood of getting that data. So in this case, we would say the notation that we would use is I give it a hat here, because again, this is an estimate. And then we would subscript it with an MLE, because there are other kinds of estimates that we could give. In this case, we've found the maximum likelihood estimate. Okay, any questions about that? Okay, then on the next page, define more generally how we find the likelihood function. And this applies whether we have a discrete or a continuous random variable. So just like we did in the previous case, we can think about multiplying the probability that we get x1, that we get x2, that we get x3, and so on. And so that's going to be our likelihood estimate. So our likelihood estimate is just what's the probability that we would get all of these values. And there are going to be some unspecified parameters in that formula, depending on how many parameters we need to define our underlying distribution. Okay, any questions? Okay, so I'd like to give you a little bit of time, even though we're in different places. I do think it's very valuable for you to try and work your way through some of these problems. So what I'd like to do is give you a little bit of time to try and come up with the likelihood estimates for these two problems. And again, what's going to be useful to note here are the PDFs for these functions, right? So what we need to find these likelihood estimates or these functions are the PDFs for the underlying distribution. And so for a binomial distribution, where we're picking n observations here, are n is equal to 3, it would be, okay, we've got one parameter here, which is the probability of a success. And just recall that these are written as 3 choose x, p to the x, 1 minus p to the 3 minus x. So that's going to be useful for this one. And then for exponential distributions, the parameter is lambda, and in this case, we've got lambda e to the minus lambda x. So I'm going to pause the recording just to give you a little bit of time to work on these. But if you're running into some trouble or you have some questions, just please chat me. You can just chat me directly, and I'll get back to you. If you think you're done, then just chat me that I'm done. That's good for me to know when people are starting to finish up. So we're not in the same room, but if you can kind of just keep me posted in the chat about how each of you are doing. I've got a question. I think I'm done. That's helpful for me. But I will just pause things for now and stick around and just let me know if you've got a question while you're working on this recording. Okay, so here's some of the work that I was doing while everybody was thinking about this. So we've got this binomial distribution. And again, what's going on here with a binomial distribution is we're running an experiment, an identical experiment 3 times. Each time, the probability of success is p, but we don't know what p is. But what we do know is how many successes we observed when we ran this the first 3 times. I did this experiment a second time. Out of 3 attempts, all 3 were successes, and so on. So here are like 4 separate samples that we collected, right? And here a sample is, for example, 3 repeated experiments, and we're counting how many successes there were. So by definition, the likelihood function we get by taking the product of these PDFs. So I need to know what the PDF is over here. And again, I don't expect you to rattle off the formulas for all these PDFs off the top of your head, but you will have a formula sheet that has these PDFs for you. So you go to the formula sheet, figure out what the general formula is for the PDF, and now we just evaluate it at each of these values of x that we observed in our 4 samples. So here is the first one. We get 3 choose 1, p to the first power, 1 minus p to the second power. And then we get a 3 choose 3, p cubed times 1 minus p to the 0 power. That's why I left that term off, and so on. So are there any questions about that? Okay, so I hope that some of those not sures are graduating into good, but it's totally normal to have some questions with this. So please just let me know if there's something that's not clear. Ultimately, what we're going to want to do is try and optimize this and do some calculus, right? We're going to try and figure out where's the critical points and so on. So, my God, my dog ate my pods, and now this thing is like fuzzing out every so often. Anyway, so it might be nice to simplify this more before we then try and do some calculus. So in the end, what we're going to get is some function that we call L, because it's the likelihood function, and now the only variable is p. And so if I group all of my constants together, this gives me like 3 times 1 times 1 times 3. So all of those n choose k's, I multiply them up together, that gives me just a constant 9. And then I can group my p's together. I've got 1p, I've got 3 more, I've got 3 more, and 2 more. So altogether, I've got 9 of those. And then I can write out how many 1 minus p terms do I have, and here I've got 3 of them. So that gives me, in this case, that would be the likelihood function for this example. Are there any questions? Okay. And in part B, what I want to be clear about here is although these values aren't specified, right, we're treating these as like some constant values, and the only unknown is this parameter lambda. So now we're dealing with an exponential distribution. So just like with discrete random variables, we do the same exact thing. We just take the product of the PDFs when we evaluate them at x1, at x2, all the way up to xn. But again, these values x1, x2, xn, these are typically things that we observe and we have like concrete numbers for them, and the lambda is the unknown. In this case, we can also do some algebra to group all these terms together, right? I've got n lambdas that are being multiplied by each other. Oops. And then I've got e to the minus lambda x1 minus lambda x2 minus lambda xn if I were to multiply all of those exponentials together, right? So when we multiply exponential terms, we add the powers together. So I'm just going to rewrite that power as minus lambda times the sum of all of the xi's. Okay, so I'm just trying to emphasize here that since the next step in this process is take a derivative and find critical points, it is often helpful to simplify this before going on to that stage. Okay, so we're kind of breaking this down into steps. So step one is find the likelihood function, and then step two is going to be let's maximize that function. But any questions so far? Okay. Okay, so now this next, yes, Ivy, sorry.
Can you go back to the part 3A? Yeah, I was just wondering how you got the 9p to the 9th. Can you go over that again?
Yeah, so this stage was okay where we had like this whole big thing here.
Yeah.
Okay. So then what we're just multiplying all these terms. So I've got p to the first power times p to the third times p to the third times p squared. So adding up, all of it, we're just kind of grouping like terms together. So grouping all of the p's together, we've got 2 plus 3 plus 3 plus 1 of them, and that's what gives us the 9 over here.
Okay.
Yeah, and same idea for the 1 minus p, we've got 2 of them here, we've got 1 of them there, so that's what gives us the 3.
Okay.
Yeah, and this 9 I kind of did a bit quickly, but if you calculate 3 choose 1, you get 3. 3 choose 3 is 1. 3 choose 3 is 1. 3 choose 2 is 3, and then we just multiply those constants together, and that gives us 9.
Oh, okay. Okay. I thought it was, for some reason, I thought it was addition for some reason. Adding,
Yeah.
like I thought it was like 8 or something like that. Got it.
Yeah,
Thank
so
you.
it's kind of, yeah, so you're kind of adding the powers of p, so that part is addition, but then you're multiplying these things in front. Yeah.
Got it. Thank you, Adam.
Mm-hmm. Are there any other questions? Okay, now I've got my likelihood function over here. And we'd like to maximize this function. And so generally speaking, right, when we want to maximize things, just to kind of back up to this graph, right, maximum values, though this is a different graph, right, they occur where graphs turn around, where the derivative is 0, or if it's a corner, perhaps undefined. So when we want to find max values, we're going to try and figure out when is the derivative 0 or undefined. And there may be several points where that happens. And then we compare those points to figure out which value maximizes that function, right? This is how optimization goes in calculus. So that's what we're going to apply here. We've got some function, this likelihood function that we want to maximize. We want to find the value of P that's going to make it most probable that we would get this sample. That's what's going on. So in this case, we can use the product rule on this, since we've got a product. So what I'm going to do is take the derivative of L with respect to P. That's kind of like, let me take the derivative of the first function times the second. And then I take the derivative of the second function. So taking the derivative of 1 minus P, I forgot something here. Right, would mean I would take the derivative of the outside function, which is raised to the third power, and then multiply that by the derivative of the inside function, which is -1. So feel free to go ahead and try and optimize this, figure out what the critical points are. I'll do the work up here and just kind of be silent. I'll silently work through it, but you can check your work with mine. But the goal here, again, is to figure out when is this going to be 0 or undefined. There's going to be there's no value of P that's going to make this undefined. So we're really just trying to figure out for what values of P is the derivative of the likelihood function equal to 0. And so there is going to be some algebra and some calculus that we're going to run into at this point. So any thoughts on how I could figure out what values of P are going to make this equation equal to 0? What could I do with this?
You can factor out a P to the 8. Or,
Yeah, so
one P to the 1 P or 1 minus P squared.
yep, let's do both of those. That's right. So whenever we're trying to figure out when is something equal to 0, usually a good idea to try and factor it. So I can factor out, for example, 27 from both of these terms. I can factor out a P to the 8th and a 1 minus P squared. And then what's left from this first term is going to be, we have a 3 and we have a 1 minus P. And after factoring all this stuff out from this term over here, what's left is going to be minus P. So now we've got this derivative in factored form. Kind of simplifying that last term is just 3 minus 4p. So this gives me 3 possible values for p where the derivative is equal to 0. Any questions? Oh, I see one in the chat. Yes, p is equal to 1 is one critical point. True. We've got 2 others now. Any questions? Yeah, so we could have identified a couple of these from the get-go. So what I can see over here is okay, what we're trying to optimize is not the derivative, right? We want to find when the derivative is 0. We've accomplished that goal. And now we compare values of the function we're trying to optimize, which is the likelihood function. So if p is equal to 0, then what is L of p going to be? What would I get for the likelihood function when p is equal to 0?
0.
Yeah, we're going to get 0 for that one. Thank you. Right, because of this term right here. If p is equal to 1, what are we going to get?
0.
0 again. Okay, so what we're seeing here is like, and keep in mind that we have a domain, right? The value for p, because it's a probability, is something between 0 and 1. So what we're seeing here is that saying that we have no successes or saying that we only get successes, these are like the worst guesses for p. And the only other option is the other critical point that we found, which was 3/4. And here, what's important is that gives me something positive. So that has to be my maximum value. And down below is the graph. And we're getting a consistent result down here that we could see when p is about 0.75, that does line up with the maximum value. And what we found over here and over here were the minimum values of the likelihood function. So what we're saying here is that the value of p that makes our sample most probable would be if p was equal to 3/4. So therefore, I'm going to say that's the most likely value for p. That's how MLEs work. Any questions? Yeah, so here's the kind of general process that we just applied, which is we find the likelihood function, and then we optimize that likelihood function using calculus, figuring out what the critical points are, which critical point gives us the maximum value of L. Okay, any questions? Okay, so let's take a look at this other one. I think that's the next question. Yeah, let's try and optimize this one over here. And so here, again, we're thinking of theta, or excuse me, lambda as the variable, and all of this stuff these are fixed constants that we would be given, right? So we collect some sample and we know exactly what those values are. And so based on those values, we want to optimize this function. Okay, this one is a lot worse to deal with, right? We want to take the derivative with respect to lambda. Yuck, right? We've got lambda to the n, and then we're multiplying by some exponential thing that has a lambda in there as well. So here's a really useful tool that we're going to do. Just going to take a detour for a second. So let's imagine in calculus, you want to have a function like f of x is equal to the square root of x minus 3 squared plus 2x cubed, something like this. I'll make it all positive, so I'll go like that. I would like to optimize this function. It's quite tricky to do that with this square root. So what we can say is that this function f of x will be greatest when x plus 3 squared plus 2x cubed is greatest. This is a really bad example because we can just make x as large as we want, and that's going to make this thing as big as we want. But the point that I'm trying to make is we have this complicated function, but I can maximize it just by kind of looking at one piece of the function, which is most important. So here the observation is the square root of something is biggest when the thing that we plug underneath the square root is biggest. Okay, and this is because this function y equals the square root of x is an increasing function. So the larger we make the thing inside the square root, the larger the square root of that thing is. Okay, a little bit of a detour, but maybe this looks somewhat familiar from calculus. Sometimes you are asked some problems like find the coordinate that's going to minimize the distance between a couple of things. And then in that case, you want to minimize something that looks relatively close to this. So the same logic here can apply to logs. And in particular, we're going to take a look at the natural log. So if I have the natural log of some expression, this is going to be largest when the thing inside the natural log is largest. And that, again, is because the natural log is an increasing function. Looks a little bit different, but it goes up as you go to the right. Okay, so in many situations, when we're working with likelihood functions, but maybe not all of them, but in a lot of situations, rather than optimize the likelihood function, we're going to optimize the natural log of the likelihood function. You might think, why are we making the likelihood function worse? But we'll see some nice properties that come out of it. And so in particular, the main point here is that it's a lot easier. We can take the derivative of sums much better than we can take the derivative of products, right? So if I want to take the derivative of, well, we'll see this in a second. So that's kind of the main idea there, is that we have some products. When I take the log, this is what I'm trying to say. Right, we have this property that says, if I take the natural log of A times B, that's equal to the natural log of A plus the natural log of B. Taking the derivative of A times B, that can be tricky if A and B are some expressions, right? We need to use the product rule. But taking this derivative is going to be somewhat easier because we can break up the sum. So there's a trade-off. We've got a log in there, but at least now the product becomes a sum. So let's see how some of these properties help us. So the main one here is that because the natural log is an increasing function, when we maximize the log of whatever is inside there, it's the same thing as maximizing whatever is inside of the log. So for this case, this is going to be an example where this might be easier, because what we actually have here is lambda to the n times e to the minus lambda x1 times e to the minus lambda x2. All of these, right? So if I wanted to take this derivative, I've got like a really long product here that I might, that we need to worry about. So instead, what we're going to do is we're going to find the log likelihood function. And one note that I'll just say is that in statistics, we use the term log a lot, log, and that usually refers to a natural log and not log base 10. So here we're really mean like the natural log likelihood function. So here, what I'm going to do, I'm just going to call this y is going to be the natural log of the likelihood function. And now we can use properties of logs that say, I can break this up. Right, using properties of logs, and I used another property of log over here that says if I have the natural log of a to the p, that's equal to p times the natural log of a. So if you were ever in an algebra class thinking like, when are these log properties ever going to have any application? This is the day for you. This is a day where these log properties have a whole lot of applications in these problems. So we can simplify this even further. Right, by saying the natural log of e to the minus lambda x1 is just minus lambda x1. And so before I go ahead and optimize this function just like before, it's going to help maybe just to simplify this a bit. So I can write that as minus lambda times the quantity x1 plus x2 plus x3, so on. Okay, that's a bunch of math so far with logs and other things. Are there any questions? Okay, now we take the derivative of this function with respect to lambda. Okay, so I am going to highlight the lambda and the lambda. Okay, all the other terms I treat as constants. So when I take the derivative of the first term here, I get n times 1 over lambda. And when I take the derivative of the second term, I get 1 times the sum of all of the x's. And I set that equal to 0 to figure out what are the critical points of the log likelihood function. Those are going to be exactly the same critical points as the likelihood function. So now keep in mind, there's a whole bunch of symbols in here. And what we want to do is solve for the parameter lambda. So I think solving that would give us lambda is equal to n over the sum of the xi's. Right, which we can write as 1 over the sample mean. Now we have some new notation for that. We call that the maximum likelihood estimate for lambda. And hopefully this makes sense if you think back to exponential distributions and the rate parameter lambda in these exponential distributions, right? Lambda was equal to 1 over the population mean. And what we're seeing here is that the best estimate for that would be to take 1 over the sample mean, which kind of makes practical sense there. So at least what's really nice about this estimate is it makes practical sense. What's the best estimate for lambda? Well, if I knew the population, lambda is 1 over the population mean. I don't know the population mean, but I'm going to replace it with the sample mean. That makes sense. That's why we'd want to do that. Maximum likelihood estimate kind of shows why we want to do that. Okay, any questions about that example? Okay, so we've got 13 minutes, which is, I think, the optimal amount of time to try one more problem together. Or at least I want you to try one more problem before we go, just to see if you have any questions. And these are the types of problems, again, that you'll have on your next homework assignment that's going to be due next week. But just to keep you on track for what you would want to do in these problems is first we're going to find the likelihood function. Which is going to be, we've got these observations. By taking the product of the PDFs. And then we're going to optimize that with respect to theta. And oftentimes this will be one of those cases, I think. Yeah. Rather than optimize the function itself, you optimize the log likelihood function. So I'm gonna just pause this and let you work, and then we'll kind of, it's 3:05 right now. Maybe I'll give you like 5 minutes to get as far as you can in this problem. It's cool if you don't wrap it all up, and then we'll spend the last 5 minutes going through it together. So I will just pause things, but I am the rest of this in. Okay, so now we want to find a maximum likelihood estimate for this data that we have observed. We've got 4 values that are coming from a distribution that has a PDF, which is given below. So as we kind of noted, like step 1 is find the likelihood function by taking the product of the PDF at 5, 9, 9, and 10. So that would look like this. So all I've done is I've plugged 5 in for X, plugged 9 in, 9, 10. Then we group some terms together, try and simplify that. So I group my like terms together. Got 4 lambdas, got my exponential terms, then I have my terms in the denominator. So that's kind of the first step in the process, which is let's find the likelihood function. Any questions about that? Okay, then this is a pretty nasty looking function. And so if your question is like, when does it make sense to take the log of the likelihood function and when do we not need to do that? Anytime you're looking at product and one of those products is an exponential, like this one over here, this is a really good candidate for the log likelihood function being a faster way of doing this. So we take the log of the likelihood function, and then we can break that up, excuse me. And using properties of logs, we can break up the products and the differences, right? So I've got this times that divided by that. So I've got natural log of this plus the natural log of that minus the natural log of that. And in addition, we can pull out the power of the 4 over here, and we can simplify the log of the exponential stuff over here, similar to last time. So the log likelihood function we can write as 4 times the natural log of theta minus theta times the sum of these square roots minus this natural log of this constant stuff. Okay, now we take the derivative of the log likelihood function with respect to theta. So taking the derivative of this first term gives me 4 divided by theta. Taking derivative of this term, I feel like my head's getting cut off. Taking the derivative of this one, right, we just give us, this is derivative of this is 1 times all this stuff. And then for this term, it looks like it's really bad looking, but there's no theta anywhere in this entire term, right? This is just a constant number. So when we take the derivative of this, we get 0. So that's super nice. Our derivative is now just 4 divided by theta minus all this stuff is equal to 0. So what's left to do is figure out what values of theta are going to make this derivative 0 or undefined. So I should say that we do have one critical value, which is theta equals 0 is a critical value because the derivative is undefined there. And then we have a second one, which we could solve for theta by bringing this stuff to the other side, taking the reciprocal and so on, which comes out to about 0.35. And then what you could do is, because we have these two values, you can come back to the likelihood function over here. This is what we want to maximize. And we can see real quickly that if theta were equal to 0, that's not going to maximize things. We're going to get a likelihood function of 0. So that means the other critical point at 3.51, that is my maximum likelihood estimate. Okay, so I will stop here since we just hit our time limit. And I'll kind of pick up with any questions that you might have with this before we get going on the new thing on Thursday. But the plan is for Thursday to kind of move on and talk about another method of estimation called the method of moments, which is also a calculus-based method. So you've got a little reading quiz for that before class on Thursday. And you've got homework that is also due on Thursday. So if anybody has any questions, you're welcome to stick around on Zoom. Otherwise, have a nice afternoon. Sorry for the Zoom situation today, but I will see everybody back in class on Thursday.
Excuse me, Adam.
Yeah, I'm just gonna